Hello everyone, it's nice to meet you finally in person. Welcome to my talk, A Beginner's Guide to Predictive Maintenance. A few words about me. Currently, I'm a data science technical lead at Relayer, an industrial IoT company. I have around 10 years of experience in data analytics and data science and a master's in mathematics, but you will not see any equations this time, I think. Okay, so to give you a brief introduction about what I will be talking about. So first, I will explain what exactly predictive maintenance is, what kind of data we use when we're handling this kind of problems, what predictive maintenance tasks there are in general, and the challenges we face, which I think is the most important part of the talk, not to discourage you of entering the field, but you know. Okay, so what exactly is predictive maintenance? When I was starting to prepare this talk, I was thinking of a good title, looking at, funny quotes and so on. But in the end, I found this very good sentence from a thinker of our times, well, maybe not exactly in our times, maybe a decade ago, that pretty much sums up what predictive maintenance is about. So Ice Cube put it better than any of us could, and this pretty much sums up the whole field of predictive maintenance. Because predictive maintenance is one of the top level of maintenance modes. So what are the maintenance modes you can ask first? So there's reactive maintenance, which is the fancy name that nobody has ever before put to what you are doing at home. You fix it when it breaks, yeah? So when you have issues with a machine, issues with something, then you fix it, yeah? You can imagine that it's not very ideal, not even at your home, yeah? You'd rather know when something breaks, and especially when you are running an industry where machines are kind of more important, yes? So then comes preventive maintenance. So you know those stickers they put on elevators, you can always see like when was the last time the elevator was actually inspected. So that's preventive maintenance. You maintain something at regular intervals, like every year, every month, whatever. If you want to be smarter at it, you can do usage-based maintenance. Yeah, so this time you track how often your machine is used. So if it's not used, why maintain it, right? It's just sitting there gathering dust, why maintain it? But for this, you need to start tracking the usage itself, and that's already a new task. Yeah, this can be sometimes a bit complicated. So enter what we are talking about here, the holy grail of maintenance, predictive maintenance. So obviously using magic and data science, you are predicting when the device will break and fix it before it breaks, preferably. So you might ask, what sort of data is used for predictive maintenance? And as a data scientist, you probably have handled different kinds of data, but how often do you think where your data is coming from? Probably not that often, yes? And in predictive maintenance, this is kind of crucial. You have these two pictures here of a real deployment of our sensors, because our data is coming from exactly those sensors. So imagine this huge, I cannot stand here for scale. Imagine me standing here being about this tall. And these two tiny things that you can see better here are the sensors, vibration, and not only sensors that are gathering the data. The S stands for Skylar, our product for rotating equipment predictive maintenance. And those sensors are gathering the vibration data and some temperature data, different kinds. I will cover it more in a minute. And they are sending those right to us, yes? So this is a bit different than the IoT you have, for example, in your phone, yeah? Like a simple function that checks how is it moving, accelerometer, whatever, yeah? So what types of data we gather? There's something that we call simple measurements. And this is just the simplest data you can think about, like speed, temperature, also aggregations of vibration data like RMS or something. What are the use cases? They are a bit limited. Trend visualization, obviously, as you can see here, chart with temperature, not much to write home about. You can do simple trend analysis with this, or some simple thresholding, like maybe you don't see this, but right at the beginning, those 40 degrees seem like a good cutoff for something dangerous and machine overheating. Yes, so this is the simple kind of data we are handling. For more complex analysis, you need more complex data. Yes, so we have vibration data. I won't cover what vibration exactly is. I'm not a physicist. Yeah, so you should consult Wikipedia if you want to learn more. But basically, it's about machine oscillating around some center. Yes, we gather for this, those sensors gather for us high-frequency samples that we can then you need to track this motion of the machine of the vibration in some ways. So there's displacement. So how does the machine move around the center? Then there's velocity, which is just the change in displacement over time, and acceleration, which is the change of velocity over time. Yes, so you probably have heard about all of these in your physics lessons. You can analyze them across domains. Like time domain is the most natural one for us to think about, but when you analyze vibration, it's better to use frequency domain. And with all of these, this is the base of multiple vibration analysis tools, like the one that vibration analysts actually use. This sort of data is, like I said, these are high-frequency samples. For each second, you will get thousands of data points. So this means that they need much more memory. They won't be, it's not a good idea to simply put all this data in a data warehouse or wherever. You need better storage solutions. Okay, so now you know all about the data. Well, not much about the data, but enough to understand what we're doing. And what exactly are we doing? So what are the main tasks of predictive maintenance? And to cover those, you can imagine what is the customer thinking when he wants to deploy a predictive maintenance solution. So first, you want to know whether there's something wrong with your machine. Yeah. So there's anomaly detection, and then you want to think, okay, but is it really bad? What's happening? Because you don't want to, start a huge maintenance when the problem is minor. Yeah. So there comes health state classification. Then you want to know what happened. Yes. So there's fault classification. So you want to know what exactly happened with your machine. And, well, I hate to say holy grail 2 times in one presentation, but there's the holy grail of predictive maintenance, remaining useful life estimation, which is telling you something better. Before the machine breaks, it tells you, okay, your machine will break in, let's say, 50 days. So you can do some maintenance before it happens. I will cover those problems a bit more now. So anomaly detection. Probably you've done it on some data, and if you've ever done it, you know that anomaly isn't always the same thing, yes? And when we look at a chart like that, it's super simple to say what the anomaly is, yes? It's that red point, if you didn't notice. But when the data is multidimensional, then it becomes kind of complicated. Yes, there are many ways of doing this, and with time series it's even more difficult. Yes, because it isn't just what is the value, but is the right value happening at the right time. Yes. Okay, so there's also the issue of those anomalies that, especially in with machines, yes, they can sneak up on you, because your machine doesn't go usually from being perfectly normal to suddenly developing this strange behavior. It usually just degrades slowly over time. So this degraded state becomes your new normal, yes? So you need to train those anomaly detection models in a way that prevents this. And in general, you never know whether just looking at the data, if an anomaly is really an anomaly or is it the expected behavior. Because, for example, a speed changing for a machine, the load changing for a machine might change its behavior, but this is perfectly normal, yes? Okay, enough about anomaly detection. We know there's something wrong, and now we want to assign this data point to some health state. Here you see some machine that's at different levels of degradation, yes, and you might already know, like, the difference between healthy and unhealthy is obvious, yes, but there's like slightly degraded machine and there's very degraded machine, and the customer wants to react to those accordingly, yes. So those thresholds between those states are difficult to calibrate. And if you want to do without calibration, you need to collect enough labels for all those states, and you don't want to break a lot of machines for the sake of that, yes. The customer wouldn't be happy. The customer won't be happy, running the device to the point of a complete failure just so that you collect labels, obviously. So you have either a thresholding problem on some score or a multi-classification problem, and these are always kind of messy. Okay, but let's say we know there's a problem, now we want a fault class, this should be easy. No, again. So here's a simple thing, a roller bearing. So you probably have seen some, and already something simple like that can have multiple ways of breaking, yes? All those faults manifest in different ways. So, and that's just one piece of equipment, and each piece of equipment has its own problems, yes, as you can imagine. And so, again, what do you need? Labels. Labels, the thing that is difficult to come by. And then even then you don't want to classify half your points as unknown, yes, because the customer won't be happy that you keep telling them that it's an unknown failure. So here's a place where we can really mix expert knowledge and machine learning methods. Yes, obviously you can use classification, but I will later tell you how exactly the expert knowledge can be deployed here. So you might think, okay, it broke, why do we care why? But imagine that you are sending a technician to a site to check on a machine. They should know who to send, and they should know what kind of tools they should grab with them. Yes, it's not as easy as you will see. Okay. And the holy grail I mentioned, remaining useful life estimation. So obviously, since it's the final thing, the most sophisticated thing, it's the most annoying one to actually estimate, yes. But it's very important because that's the only way to actually avoid this downtime. Even if we catch it, we don't want the failure to happen, even if we really are desperate for collecting labels. The customer won't be happy, yes? So it's very difficult predicting when a device is likely to break because you need multiple runs of the same device to extrapolate when it's going to break, yes? This is a very complex problem, one that I won't get much into here, but yes, this is something that where you can really believe that the value for the customer is the biggest. Okay, so what are the challenges we face that I promised in the beginning that this is going to be the main part of my presentation? So here comes another quote from a person much less famous than Ice Cube, but I think you are going to be more familiar with her. Sensor data, this should be easy. These were my famous last words before joining Relayer. Because I came from the world of business intelligence, customer intelligence, where I thought that, well, I was analyzing humans. Humans are messy. Machines should be much easier, right? Machines should come with labels. When a machine breaks, everybody should know that it happened. Okay, so why is it much harder than expected? So here's the world of business intelligence, obviously idealized for the sake of the slides, and there's the world of predictive maintenance. Let's imagine that we have a website, yes? So you have a website, the data should be more or less readily available, yes? You had databases and so on. That's how you even have a website, right? With predictive maintenance, you need to place this sensor and you need to place it correctly. You cannot just stick it anywhere on the machine. You need some expertise, right? And there's this thing that you might imagine the factories to look a bit different than that they actually look. I will come back to this later, but the sensors really need to be placed correctly at first, yes? Okay, I mentioned websites, databases, relatively clean data. Don't correct me that the data is messy anyway. This is just an example. And with machines, you can imagine that, you cannot just, if your customer makes a purchase in a noisy environment, you're still getting correct data. If your machine works in a noisy environment, you will get all the noise inside, yes? So that's the problem. And like if you've got a website and you want to say, okay, let's track something new. I want to track what browser the user is using. Then it's relatively easy to modify the acquisition software, yeah. With a sensor, the sort of data you can gather is fixed, yes. So that's a different thing, yeah. And yes, when somebody buys something from your website, you see it right away. If they click it, you see it right away. And, well, you will only get data about machine failure when the machine fails, obviously. And there's the final thing. So if you ever analyzed a if you ever anybody here used a website, like, clicking something online? Anyone? Nobody? Oh, yeah, one guy in the front. Yeah, so everybody knows how websites work. But for predictive maintenance, you actually need expert knowledge. That's a huge shock for me. Okay, so here are some of the problems I have mentioned so far. So lack of labeled data. Why is there an omelette on the side? Yeah, because you cannot make a model without breaking a few machines. Just like you cannot make one omelette without breaking eggs, yes? So, and like I mentioned continuously, customers don't want their machines to break. Well, yeah. So, even when the machine breaks, they don't want to tell you. They want to go and fix the machine. Telling you is the last thing on their minds. Yes. So you need the data from somewhere, but it's not like you can just extrapolate from one machine to others because different machines with different settings will produce very different data. And you might use some publicly available data sets, but they don't usually align with your needs. Yes, ask me, I tried. Okay, so what are our solutions for that? So you can develop solutions first to encourage the customers to give their feedback. So when they are informed about a problem, they are also asked, yes, please tell us if there was a problem, obviously. You can use some rule-based weak supervision, but that's a pretty generic solution. You can label data yourself or actually using some expert. Creating some artificial data sets is difficult. It's not very easy for the sake of problems, but you can also purchase a test bed. That's a shot of our test bed that we've recently purchased to produce the data, label data for yourself, yes? Okay, another problem that I mentioned is the domain knowledge. Yes, there's no need to reinvent the wheel. Even if a data scientist, you will be very, you will want to do this a lot. But there's a lot of existing knowledge. There are standards and some industry standards that are used, some thresholds, for example, for when the machine is supposed to be breaking. But in general, the biggest thing that you can leverage here is the vibration analyst knowledge, the tools that they are using. In general, every time you tackle a machine learning problem, you want to know how a human would have solved it, yes? Because if the human knows how, where to look, you should also look there instead of, as I said, reinventing the wheel. And the challenge lies in transferring this domain knowledge into code. And thankfully, there is this whole field of signal processing that can help you. So about leveraging this knowledge, I will share an example with you. So like I mentioned, those roller bearings are very complex. Here come the formulas, okay? But they are not actually mathematical formulas. That's physics, even worse. So a simple element like that can break into multiple ways, yes? And there are ways, like these formulas tell you where exactly look for these faults, yes? And this becomes quite easy, yes? Because here you have the promised frequency spectrum. And as you can see, those red marks show roller bearing harmonics for outer race fault. So the vibration analyst knows that if there's a peak in frequency spectrum at those frequencies that are repeated, then there's a problem, yes? And imagine you trying to teach a machine, a model, yes, to recognize those. Why should you? You can tell the machine where to look at those, yeah, with just a simple rule. So then it becomes very easy, yeah? You need to know what variables to actually use, yes? No need to try and find a pattern in some other way. Okay, another thing I mentioned is data acquisition itself, yes? So here's that promised picture of a factory, yeah? So the modern factories don't really look like that, like this 19th century or maybe even earlier example. Imagine that you have a site where you need to, when you want to travel to some machine, and it takes a person in a car 2 hours. That's one of our customers. They're not going to go and check something because you're just thinking, okay, this might be a false positive, but check it for me. And they're not going to go and check something for you, like never, yeah? And once we deploy our solution, once we place those sensors, they just expect it to work, right? And the problem is that different sensors can collect data in different ways. So actually, there's no standardized ways of this. You cannot send the data all the time because then you would be replacing batteries all the time, and it all costs energy. Even I think with our current typical deploy, it's like if you collect the data every 6 hours, the battery will run out in like 5 years or so, yeah? So imagine it's already just 4 times a day, yes? So there's this balance, and there's lack of precise metadata. You've seen all those fancy formulas for those roll bearings. So imagine you don't have those numbers you put in those formulas, then they are useless, yes? And it's usually, like I said, you can only deploy once. But then what happens when you can't deploy the way you want? Like for speed, there's one easy way to deploy a speed sensor, but those sensors cannot be deployed on any machine, yeah? So sometimes you can't just do it the correct way, the easiest way. So what are the best practices we can follow here? So have very strict sensor onboarding policies, obviously. You need to make sure that the algorithms you train don't just work on the test data you're giving them, that they will actually work on the data you're getting in production. And you need to plan ahead, like what is needed right now, but what else you might need in the future, yes? You need to select the right sort of hardware, yes? You don't want a shitty sensor that will die in a year, yes? You don't want a sensor that's going to be having a lot of lag because then the information will become useless for the customer, yeah? And how to solve all those problems is, again, consult a vibration expert or two. And here's actually a picture, a very anonymized picture of our one of our vibration analysts, Tunç. And this is actually how these guys work. Yeah, they work on site. This is, funnily enough, occupation that moved from blue collar to white collar when computers started tracking the data. Yeah, there's no need to check something on site because this way you are going to gather the data on a computer without all these problems. So the expert knowledge from guys like Tunç is super crucial for us. Okay, to sum this up, predictive maintenance in 4 quick lines. So predictive maintenance is currently one of the biggest trends in industrial IoT. It requires a lot of expert knowledge, as you've seen, and comes with a lot of unique and sometimes quite unexpected, at least for the people who come from outside the industry, challenges. But to be quite honest, it's also a very fun field to work in, even if you don't get to visit this factory and do this 2-hour ride to the broken machine. Okay, thank you. So this is all from me.
Thank you, Marta, for this great talk. I don't know whether you know, but Marta is from Katowice, the same lovely city as mine. And yes, it was very, very cool. And how about the questions? Let me please take a look.
And one of those dots on this map, yes, like hard to notice, but Katowice is one of them.
Okay, and the next Data Science Summit will be held in Warsaw, of course, but you know. Okay, let's switch.
I cannot choose, this is too difficult. Can I get any simpler questions, like something about physics or vibration data, yes?
Yes, and yes, we have 5 votes. I'm gonna show you the results. That's okay. And the questions, right? The questions are here. Live questions. But I have to deactivate the vote so that you can see it. Boom. Yeah, finally you can see Marta. And the first question is... Yes, we have another question. I love this app, but let me please start with this first one.
Basically, you can't use a machine that's already broken, yes, because you need the vibration data from a running machine. Yeah, so that's the issue. You need to catch the breaking moment of the machine or the degraded time, yes. And with a test bed, you can do whatever you want, but we actually get most of our data from our customers, yes. So from the live deploys. And for the second question, I hope it answers the questions. For the second one, yes, like I said, temperature with motor currents, we also want to start using these. Like I said, not all data is readily available with every sensor, but this is something that we also want to track in the future when we start focusing on electric motors more. Okay. Yes, we do, but not on my product. So in general, in the company, we use edge computing, but not on the product I have. Some of the edge computation is actually done by the sensor company. And this is and some is done by our IT, but as in my product, there's no edge computing for models themselves. Yes, just some calculations of metrics and so on. I couldn't tell you right now. Yes, that's. I would have to honestly check because I joined the company with already some of the things already there, so not part of what I worked on. But I can reach out. If you reach out to me later on LinkedIn, yeah, we can talk. Yes, we use sound, but I cannot tell you much more about this. Yes, we use anomalies for sound, but yes, this is like I cannot give you details.
All right, these are very nice answers, quite quick.
Yeah,
And my question from my side, how do you feel?
good.
Cool.
Yeah.
See?
But there's one more question. I have 20 seconds. Yes.
Bravo! And still 11 seconds to go. Maybe there are questions from the audience. Please raise your hand, press the button. Yes. And how about the button?
3 seconds. One.
Running,
late.
running.
Thank you. Quick question. Suppose you have a machine that has already broken. You predicted it's going to be, actually no, you predicted the machine is going to break in 50 days.
Yes.
You send the maintenance team, they fix it. So how can you say that you were actually right? What's the method of evaluation of work?
You know, this is the kind of problems I really love, because when we are right, then the machine, and they don't react, and the machine breaks, it's a success for us. And if we are not right, they fix the machine and it doesn't break, then we are also right. Yes. So no, but really we validate the data afterwards. Yeah, because sometimes there are like obviously you cannot tell. That's the main problem with problems like the main problem with stuff like this in general. Yes, like also predictive customer churn. There's no uplift methods we are using here. Or if they don't react, the machine will break. If they reacted, the machine wouldn't break anyway. Yes, that's the issue. The customers really would rather be too cautious than risk a failure. Yeah. So they would rather see rare false positives than, false negatives. It's difficult to say, yes, but I think this is quite usual for data science, for this thing to occur that we cannot exactly know. It's practically a constant, yes. Whether the customer would buy even without seeing the banner, whether have we stopped the customer from leaving, or was he never going to leave? Have we fixed the machine, or was there nothing to be done and we fixed it for no good reason? Yeah, difficult to say.
Okay, and the last question is here. Do you build digital twins of machines?
I know that our solution architects are working on this. This is an ongoing project, at least in our product, yes, Skyla that I mentioned. So yes, but I'm not involved. I can give you the phone number of the guy who does it, though, if you're very interested.
All right, thank you again. Bravo.